Hey guys, on to the last video for our force unit, Newton's third law. Now this is the easiest law to use, but also the most misleading. Newton's third law states that if you apply a force to an object, the object feels the same force as the thing applying it. So essentially, the common phrase is every action has an equal and opposite reaction. So if you kick a soccer ball with 2 newtons of force, the soccer ball feels 2 newtons of force, so does your foot. We use agent-object notation in order to write Newton's third law, and essentially what it says is force of object A on object B is the opposite value of the force of object B on object A. So if you have a book sitting on the table, the force of the book pushing on the table is the opposite of the force of the table pushing on the book. So that opposite, or that negative sign, essentially just says that it's in the opposite direction. If the force of the book is pushing downwards on the table is pushing upwards on the book. So equal and opposite. We can also label a force as an action force and a reaction force. You normally think of the action force. So for a basketball hitting a backboard, the action is the basketball on the board. The reaction is the board pushing backwards on the basketball. So the object hits something, and that something essentially hits it back. And that's because that backboard isn't moving. So he's kind of pushing back at the basketball, saying, I'm not going to move, so you move instead. So action-reaction examples. A car hitting a wall we are going to break down into the action force and the reaction force. So the force you normally think of is the car on the wall. The car pushes against the wall during the collision. The reaction is the wall pushing back onto the car. The wall might crumble, but essentially it won't move. The car is the thing that's going to either stop its motion or possibly bounce backwards. When you're walking, if we have an action force and a reaction force. If you think about the action of walking, you are pressing down onto the ground in order to propel yourself forward. So the action is your foot pressing on the ground, and the reaction is the ground pressing upwards on your foot. So if you don't have friction and you can't grip with your shoes or with your feet, you're not going to do much walking. You have to be able to push downwards or even backwards depending upon what point of your walking motion you are in. But the ground essentially pushes you forward, saying, I'm not going to move, you go ahead and move. So how do these work in calculations? We break down and use Newton's second law to solve Newton's third law questions. So we're going to go back into that F equals ma idea. We're going backwards in time to the easier math. The only new part of this idea is that the forces have to be equal to each other. So we're essentially going to be setting 2 of these equations equal to each other. So as a practice example, 2 ice skaters push off of each other while performing a routine. They push off with a force of 200 newtons. If the guy has a mass of 75 kilograms and the girl has a mass of 55 kilograms, what is the acceleration of each skater? So I'm going to go ahead and drop a line down the center of this because we're essentially going to do 2 problems in one. We're going to use F equals ma for the boy and F equals ma for the girl. So on the boy side, we're going to list our knowns and unknowns. The force is 200 newtons, the mass is 75 kgs, and the acceleration is our question mark. So 200 equals 75 times a. We have to divide to separate that 75 and that a. So the acceleration is 2.67 meters per second squared. Now on the girl side, we are going to do the same thing. F equals, m equals, and a equals. We have the mass of the girl being 55 kilograms. A is still our unknown. But they only gave us one force in the problem. Since these are equal and opposite reactions, that force gets plugged in to both F variables. So we have 200 equals 55 times A We're going to divide out, and A equals 3.63 meters per second squared. So it should make sense that as you are ice skating on the ice, if a boy and a girl push off of each other and the boy has a higher mass, he will have a lower acceleration. The girl has a lower mass, so she should have a higher acceleration. I use the same example if we talk about a ballerina and a football player. If a ballerina is going to try to tackle a football player, she's likely to just bounce off because the football player tends to have a higher mass than the ballerina. So here it should make sense that the boy with a higher mass has a smaller acceleration. Now we're going to look at this problem a little bit differently. Two ice skaters push off each other while performing a routine. If the guy has a mass of 75 and an acceleration of 3.2, and the girl has a mass of 55, what is her acceleration? Now we can do this in two separate problems again. I can drop that line down the middle and we can do the boys' math over here and the girls' math over here. But I want to look at it slightly differently. I want to set those two forces equal to each other. So the boy pushing on the girl equals the force of the girl pushing on the boy. And we can substitute both of these values for MA as long as we have the boy information on the left and the girl information on the right. So I'm going to put the mass of the boy and the acceleration of the boy, the mass of the girl and the acceleration of the girl. The mass of the boy is 75 and the acceleration is 3.2. The mass of the girl is 55 and the acceleration we don't know. So we have 75 times 3.2 equals 55 times A. 240 equals 55 times A. Now we have to divide out that 55. And A equals 4.36 meters per second squared. So we were able to do a similar calculation in one step instead of breaking it down into two. If we wanted to break it down into two steps, and we draw the line down the middle, we would do F, M, A, and we have the 75 and the 3.2. And we would solve for the F to be 240. And then on this side, we have the F, the M, and the A. The mass is 55. The force has to be the same, so 240 gets plugged in over here, and we can solve for the acceleration. Now, I don't care how you want to do these problems. If you want to do it in two steps, like you see here, or in one step, like I just erased, that's completely up to you based on what makes sense. But what we're going to do is get together in class and we're going to practice these. But keep in mind, these are areas that tend to give us some trick questions because the forces have to be the same. The reason that the objects react differently is based on their mass, not because the force is different. So when you go to apply a force to open a door, your body has a higher mass than the door does. That's why the door is the object that moves. But if I were to say you apply a force of 5 newtons onto the door, what force does this door apply onto you? The answer should be 5 newtons. So they seem like they're too easy, and they seem kind of like trick questions, but think it through, and as long as the total forces are equal, you should be good. So I'll see you tomorrow so we can go ahead and practice with this.